Now let's look at a concept called independent events. Okay. Two events are supposed to be independent if the occurrence of one event does not affect the probability or does not change the probability of the other event. If A and B are independent, then probability of A given B, okay, shouldn't change from probability of A. Probability of A should remain the same because A is independent of B. Doesn't care. I mean, if B, whether B has happened or B has not happened, it doesn't affect the probability of A. So in that case, then we can apply this into this formula that we saw before. So probability of A given B is probability of A itself. So probability of A times probability of B, if that is equal to the joint probability, then the two events are independent. So one way of verifying whether two events are independent is to multiply the marginal probabilities. So these individual probabilities are also called marginal probabilities. So if you multiply the marginal probabilities and check it against the joint probability, if they are the same, then the two events are said to be independent. Okay. If you want to say this the other way around, if you already knew that A and B are independent, then you can compute the probability of the intersection or the joint probability. You can compute the joint probability by multiplying probability of A and probability of B. A related concept is mutually exclusive events. Okay. Mutually exclusive event is that there is no intersection. Intersection is 0. So in a Venn diagram, so A and B are separated. Now you see, in the case of mutually exclusive events, if you know that A has occurred, then probability of B given A is 0 because there is no area here that A shares with B. So if you know that B has occurred, then you know that A cannot occur. Probability of A given B, if A and B are mutually exclusive, is 0. So that means they cannot be independent. So what is independence? Independence is whether a particular event has occurred or not does not change the probability, right? If B has occurred or not, doesn't change the probability of A. But in the case of mutually exclusive events, if you know that B has occurred, then we can with confidence say that probability of A is no longer what it used to be, it is now equal to 0. So independent is the opposite of mutually exclusive. Now there is one more concept which is related to mutually exclusiveness, and this is important for Bayes' theorem, and that is mutually exclusive and collectively exhaustive. So for example, if you see here, suppose if these indicate different events, B sub 1, B sub 2, B sub 3, all the way through B sub k. Okay. So now there is no intersection between any pair of B sub 1, B sub 2, or B sub 1, B sub 3, or B sub 2, B sub 3. There are no intersections. Suppose if this is your Venn diagram, right? There is no intersection between all pairs of B sub I. So intersection probabilities are all 0. So that means they are mutually exclusive. And suppose if this B1 through B sub k represent all possible events, so that means the sum of the probabilities, suppose if all of these B's represent probabilities, then if you sum all of them, and that's equal to 1. So that means we have a situation where we have pieces of probabilities and they represent the whole, and when you add them all up you get 1, and individually they don't have any intersection. And such a scenario, we call those events mutually exclusive, there are no intersections, and collectively exhaustive because the probabilities sum to 1.